Log on, tune in, find out. Another good idea from Cambridge.
The presentation of Euan Spence from Bath. And his presentation has already been announced 2 days ago in connection with properties of integral operators for scattering problems. This is his topic, and he's going to present us latest results on coercivity of boundary integral equations and operators. So please.
Thank you. Is this on? Microphone? Yeah. Okay. Good. Okay. So this is joint work with Timo Bethke and Simon China-Wild from the University of Reading, and Ivan Graham and Valery Shmizlayev from Bath, because we have a joint project between Bath and Reading on these high-frequency problems. Okay. So here's the problem I'm going to be considering. Okay. So it's the acoustic scattering problem we've seen many times before in this conference. So I have a plane wave hitting an obstacle omega and scattering off, and the total field satisfies the Helmholtz equation in the exterior of the obstacle. So here I've drawn a rather nice, simple, sort of smooth, convex obstacle, but I'm going to be considering cases where the obstacle is not so nice, and I'm going to be talking about both 2 and 3D problems. The dimensions will be both 2 and 3D. And note, I'm taking the simplest boundary condition on gamma, the surface of the scatterer, that of sound-soft scattering. Okay, so I'm interested in this problem when the frequency or wave number k is very large. And as we all know, this means the solution is highly oscillatory, as represented by these little wiggly arrows here. This high-frequency Helmholtz has lots of practical applications, but when you go and solve it with finite element or boundary element method, you find you need to increase the number of degrees of freedom to maintain accuracy, and we heard a lot about that in this the first talk this morning. So, for example, in the boundary element method, in standard methods using approximation subspaces with piecewise polynomials, you need to increase the number of degrees of freedom n like k to the d minus 1 as k goes to infinity. And the cost of the method, if you use a fast multiple method, you can get it down to about order n, which is great, but it's still increasing as k goes to infinity. And this puts these the very high frequency problems out of reach of standard methods. So the idea to combat this is to incorporate the oscillation of the solution into your method. So and lots of people have been doing this in lots of different ways recently. So one way in particular is you can try and use the asymptotics of your solution u as k tends to infinity, use these asymptotics to work out precisely the part of the solution that oscillates rapidly, and then only approximate the slowly varying remainder with your numerical method. And the goal is that you want to get methods where you don't need to increase the number of degrees of freedom as k tends to infinity, and also that the cost doesn't need to increase as k tends to infinity. So these methods formed a large part of the original HOP program and have been well represented this week by great talks about both finite element methods and boundary element methods. And I'm going to be talking about these boundary element methods. So I should note here that I'm going to be talking about Galerkin boundary element methods, whereas some of the key results in this area have been obtained in a non-Galerkin context. So, for example, the Nystrom method of Oscar Bruno, but I'm not going to be covering that case here. Okay, so broadly speaking, there are 3 numerical analysis tasks for these hybrid asymptotic numerical methods. So the first is to design the subspaces which incorporate the oscillation of the solution, with the goal that the number of degrees of freedom doesn't need to grow as k tends to infinity. So yesterday in Fatty's talk we saw that you can get sort of n growing like log k or k to the epsilon, where epsilon is small. Then the second thing you need to do is you need to implement these methods with hopefully the cost of only order 1 as k tends to infinity, and one difficulty in this is you need to compute highly oscillatory integrals. Then finally, you'd like to prove error bounds on your solution that are explicit in the wave number or frequency k. And it's this third point here that I'm going to be talking about today. So here's the outline of my talk. So first I'm going to give a quick recap on the boundary integral equation methods for the acoustic scattering and the standard methods that you use for proving error estimates. Then I'm going to talk about this property coercivity, because it appears this is the only way to obtain these k-explicit error estimates for hybrid methods. And not a lot is known about coercivity, so I'm going to then present at the end some initial results about proving this property. And the way these results were obtained was that we took some ideas, some tools developed for the analysis of scattering problems from a non-numerical point of view, carried out in the sort of 60s and 70s, and we applied these to this numerical analysis problem that in hindsight is kind of completely natural, but we didn't actually realize we were doing this to start with, although we do now. Okay, so here's boundary integral equations. One way of getting them is via Green's integral representation that gives the solution u as an integral over the boundary involving the unknown Neumann boundary value, the du by dn. And evaluating both green and its normal derivative on the surface of the scatterer gives you two integral equations involving the unknown Neumann boundary value, where this S is the single layer potential and d primed is its normal derivative. Okay, so it's very well known that each of these two equations is not uniquely solvable for certain discrete values of k, so the standard way around that is to take a linear combination of them. So what you do is you take the second one minus I eta the first one to get the standard combined potential operator A written here. And at this stage, I'm just going to note and put up here, because I want to go and come back to it later, that so this standard combined potential operator A arises from taking the normal derivative of u on the boundary, so that's n dot grad u, and subtracting I eta u on the boundary. Hopefully that's visible. Okay, so this is A. It depends on k through the single layer potential and its derivative, and on this coupling parameter eta, right? And the commonly recommended choice is to take eta proportional to k, or k for when the frequency k is high. And one of the achievements of one of the results coming from the first HOP program was that this was backed up to be kind of near optimal in some sense in this case. So here's the integral equation I'm going to solve, and from a practical point of view, I want to work in the space L2 because because this space is self-dual, you can use the same trial and test spaces, and this is absolutely okay because you have a result that says the unknown v, that's what I'm calling du by dn, is in L2, and A maps L is bounded and invertible on L2. So everything's okay. So when I solve this integral equation with the Galerkin method to get some numerical solution Vn, what I want to prove is this thing in blue called quasi-optimality, which says that the error I incur is less than or equal to some constant times the best approximation error. And my task for the rest of the talk is to prove quasi-optimality holds for the Galerkin method when you use a hybrid space Snk, so incorporating the k asymptotics, and I want to know explicitly how the constant c depends on k. Okay, so how do you go about proving quasi-optimality for boundary integral equations normally? Well, there's a classic theory that says if the boundary is C1, then A is a compact perturbation of the identity operator, and this property can be used to show that if you use approximation space of piecewise polynomials, then you get quasi-optimality once the dimension is greater than a certain threshold I'm calling n naught. However, these arguments don't tell you how the constant c depends on k or on how the threshold depends on k, so they're useless from the high frequency point of view, and they also can't give you anything useful about when you use a hybrid space instead of just piecewise polynomials. And all this is because the perturbation contains k, and that's the source of the problems. Now, there's very recent work by Marcus Mellink on a new k-explicit perturbation argument. So if the boundary gamma is analytic, he's got a very, very clever operator splitting that gives you quasi-optimality for piecewise polynomials with everything k explicit. So this is a fantastic result, but unfortunately it doesn't work, or at least it's not obvious it's going to work for these hybrid spaces S and K. Okay, and so here actually I'm just going to remark that perhaps surprisingly there is still no theory for these second kind integral equations on a general Lipschitz domain in L2, because all these previous results rely on some degree of smoothness of the boundary. So this is still an outstanding problem. Okay, so what we're going to do is we're going to consider the integral equation AV is F in its bilinear or variational form. So here's this bilinear form, and then here is this is what the Galerkin method is. And as is well known, if you can prove that your form satisfies continuity and coercivity, these two properties here, then you get quasi-optimality for any subspace whatsoever, in particular a hybrid space. So this is what we want. So then it means that the challenge for us is to find out for what domains can we prove these two properties here, and how do the constants beta and alpha depend on k, because that c, the constant in quasi-optimality, is then given by the ratio of beta over alpha. Okay, so the first property of continuity is well established and well known. Again, that was lots of work on that was done in the first HOP program. But the limiting factor is this property of coercivity. So that's what I'm going to focus on now. So what is known about coercivity? Well, when the domain is the only direct result known is that when the domain is the circle in 2D or the sphere in 3D, coercivity holds with constant 1/2 for all k sufficiently large enough. And this result was proved using Fourier analysis specific to the circle and sphere, and so doesn't immediately, or it's not easy to generalize this to other domains. Now you can deduce some things indirectly about coercivity, because if coercivity holds, then the constant satisfies this relationship with the norm of the inverse of the operator, and there are some results about certain domains for which this norm of the inverse blows up. So it doesn't tell you if it's coercive or not, but it does tell you that the coercivity can't hold uniformly in the frequency k. And then there was this numerical investigation of coercivity that Timo talked about earlier in the week, where on the basis of numerical experiments, we conjectured that coercivity holds with a constant order 1 in k whenever k is large enough, whenever the domain is non-trapping. Okay, so recall the definition of trapping. Okay, so a domain is trapping if whenever you send rays into the domain and they reflect according to this angle of incidence, angle of reflection, then if there are arbitrary long paths where the rays remain in the obstacle and don't come out again, that's a trapping domain. So obviously a non-trapping domain is when all the rays eventually escape. So you have some sort of physical reasons why you expect these domains to be nasty, and it looks like that this is the property, this is the condition under which coercivity will hold, non-trapping, and the ultimate goal is to prove this. Okay, so for the last part of the talk, for the rest of the talk, I'm going to introduce some results about proving coercivity, and these results I'm going to talk about are all motivated by a simple argument that involves Green's identity. So I should say I'm going to try and cut down on the gory details and just give you the ideas. Okay, so here's this simple argument that motivates what we're going to have. So here's my domain omega with boundary gamma and a normal n. And I'm going to introduce a large circle of radius r because I want to be careful about infinity. And so Green's identity tells me that if I have some function on some domain D, then this identity here holds. And what I'm going to do is I'm going to choose u to be a particular solution of the Helmholtz equation. I'm going to apply, so this term here is n0. I'm going to apply Green inside the domain, and then apply it outside the domain but inside the ball of radius r, and add these up and see what I get. Okay, and the particular solution of Helmholtz I'm going to choose is U being the single layer potential with density V. So I do this, I apply green inside, apply green outside, I let R tend to infinity, and just after a few lines of calculations using the jump relations for single layer potential U, I get that the real part of minus I SV comma V is greater than or equal to 0 for all V in L2. Okay, so this is a well-known result, but we looked at this and said, well, here we've got information about part of our boundary integral operator, right? So here this is the coercivity we want to prove, and here we've kind of got information about the final bit of it. Is there some other more fancy identity we can use instead of green that will give us information about more of it or even all of it? So we looked around and as to what other identities were there out there for solutions of the Helmholtz equation. And one way of sort of understanding identities is casting them in a sort of multiplier method framework. So here in this, you choose some operator n, multiply the PDE by nu bar. The bar is just to kind of keep things so you get norms out, modulus is out at the end. So you do this, and then you integrate by parts to get some divergence terms and some non-divergence terms. So in this setup, green's identity just corresponds to the multiplier nu being u. Now, another common multiplier, choice of multiplier, is nu being a derivative of u. In particular, this derivative in the radial direction x dot grad u. And these give rise to relic identities, which have been used quite a bit in analysis and numerical analysis. However, there's an identity that's closely related to the relic identity, but much less well known, and that's due to Moravitz and Ludwig. And here the multiplier is this mu, so m for Moravitz. And so here the first term of this multiplier is also x dot grad u, but I've written it in this funny way so that you can see that the other terms in the multiplier correspond to the large R behavior of u when u is a solution of the Helmholtz equation. So recall, so this first term here, x over r dot grad u, this is du by dr, and in 3D, this is order 1 over r as r tends to infinity. And if I take off IKU, then this combination, well, this is the radiation condition, this is order 1 over r squared as r tends to infinity. And then this final third term here is exactly what you want to subtract off the next order behavior. Okay, so when you apply one of these identities, you have these divergence and non-divergence terms, and what you want to prove estimates is that you want all the non-divergence terms to be single-signed. And in the relic case, this is true, and that's why these relic identities have been so well used. And in the Moravitz and Ludwig case, this is also true. Now, our argument involving green, I just told you about, it's nice when you're doing that argument if the large circle at infinity, or this large circle of radius r, tends to 0 as r tends to infinity. But for the relic identity, this is not the case, and this is a problem already encountered when you're using these relic identities for solutions of Helmholtz in exterior domains. However, for the Moravitz and Ludwig identity, because you've subtracted off these extra terms, this large circle does go to 0 at infinity, which means it's perfect for applying our argument. So what we do is we take the Moravitz and Ludwig identity, apply it inside, apply it outside, add it up, see what we get, and after a little bit of work, what you do, what this gives you, is it proves coercivity of an integral operator closely related to A. Okay, so here in the box, here is the integral equation, or the integral operator that I know is now coercive, and we call this the star combined potential operator because it's coercive for all Lipschitz star-shaped domains. Okay, and here at the top, I've showed you how to prove that your solution V satisfies this integral equation here, and you see this is why I wrote up that the standard combined potential operator comes from n dot grad u on the boundary, because all you do is you replace your n by this vector x, where x is the position vector relative to the position vector relative to the origin from which the domain is star-shaped. So the only terms that are different from the standard combined potential operator are this x dot n, and then this term here, where this grad gamma is the surface gradient. So it's the surface gradient of the single layer potential. So kind of remarkably, this integral equation is coercive for all k, not just in the high frequency case, for all star-shaped Lipschitz domains. If you choose the coupling constant to be, so some choice, it's proportional to k, but with some extra bits. Okay, so a natural question is, well, how much harder is this to implement than the standard combined potential operator? And it's not too hard to prove that the condition number is no worse than the standard one. And the only possible difficulty in implementing it is this grad gamma of s term, because this grad gamma of s, this integral operator has a singularity. It must be understood in the Cauchy principal value sense. However, if you're doing the Galerkin method, you can integrate, you can take the derivative onto the test function, and this means it's completely, well, it's as easy as the standard one. And so Tatiana Kim, the PhD student in Bath, we've now got some results which show this is then realized in practice, this convergence of the Galerkin method. So on the one hand, I've cheated because I've modified the integral operator. However, we're still quite happy with this result because as far as we know, it's the only result about convergence of the Galerkin method for a second kind integral equation on a general Lipschitz domain in L2. Okay, so still you might say, well, okay, I like the modified operator, but you know, my PhD student wrote my code and I can't change it to implement the star combined rather than the standard one. What can you tell me about the standard combined potential operator? You know, can this argument be rescued? Well, the first thing to notice is that when the domain is the circle, this operator reduces to the standard combined potential operator, because so if I have the circle, you see x, the vector field x, is normal to the boundary. So x dot n is 1 and x dot grad gamma is 0 because grad gamma lives in the tangent space. So this then gives you alternative and simpler proofs of coercivity for the circle and sphere. So then what we thought was, well, okay, since we need, this sort of x dot n to be 1 and x dot t to be 0, where t is any tangent vector, and this is only true for the circle, why don't we replace x by some more general vector field z in the Moravec and Ludwig identity? And so here is the Moravec multiplier m, and so instead we said, well, let's choose some more general multiplier, kind of curly z, where we replace x by some general vector field z. And these scalars r and a half, we also replace them by some more general scalar functions. So this idea of using more general vector fields in relic identities has a precedent. So for example, the famous work of Netschas. But we thought that we were the first people to do this for the Moravec Ludwig identity. Although recently we actually found out that Moravec later did consider more general multipliers herself, although for different purposes. So I thought I should say that in case Moravec is watching via the live streaming on the internet. Okay, so to use this more general multiplier for our argument, we need three things. Well, we need that the vector field z is the normal vector on the boundary. That's to get the standard combined potential operator. And this phi is going to be our coupling constant eta. Then the second thing we need is that we need this multiplier to look like this multiplier as r tends to infinity to get this decay property of the large circle. And then the third thing we need is we need still to make sure that all the non-divergence terms of the identity are positive. And that's this third condition here. And so far, we've managed to satisfy all these three conditions when the domain is strictly convex and smooth in 2 dimensions. So what we have then is we have coercivity for large enough k and coupling constant eta, and this is proved for any coercivity constant a little bit less than a half. And the hardest thing is to construct this crucial vector field z, and in this case we use tools from convex analysis and some geometric arguments. And we're making good progress in extending this result to more general domains and 3D as well. Okay, so that's the end of my talk. So a summary, I've talked about these boundary integral equation methods for high frequency acoustic scattering. If you can prove that the integral operator is coercive, that's this property here, then this is great because it gives you k-explicit quasi-optimality for any approximation space. So this holds for both for piecewise polynomials and the standard methods, and also for these hybrid spaces. The conjecture that was backed up by numerical experiments was that coercivity holds in the high frequency limit whenever the domain is non-trapping, and that the first results we have on proving rigorously coercivity is that the standard combined potential operator A is coercive for 2D smooth and strictly convex domains. However, if you're willing to modify your integral operator slightly, you can get coercivity for all k for Lipschitz star-shaped domains in 2 and 3D. Okay, thank you.
So, we've got a few minutes for questions, please.
Thanks so much. I have 2 questions.
Mm-hmm.
Just to understand your term trapping.
Right, yeah.
Does that correspond to 0 eigenvalue of your linear operator, or what's?
Right, so there are these results about in the 60s and 70s there were lots of investigations about characterizing trapping in terms of resonances. So these are the scattering poles of the operator. So the solution operator to the Helmholtz equation is analytic as long as the imaginary part of the frequency k is positive. But if you then allow the imaginary part of k to be negative, you get these resonances or scattering poles. And for a trapping domain, when the domain is for trapping domains, you often get a sequence of these poles which converge to the real axis. So this is the complex k plane, and you have these poles, which are these resonances, and there's a sort of complex relationship, but roughly speaking, when the domain is trapping, you get a sequence converging to the real axis. And this is saying that when the waves get when the frequency is higher, you're almost getting trapped modes.
Okay, so you don't really hit the axis, but you...
Right, yeah, so you can never hit the axis, but you can get these almost trapped modes.
Yeah, okay, that works perfect.
Right, but so the relationship is actually quite complicated, and there was this conjecture. So Lax and Phillips conjectured that the domain was trapping if and only if you have a sequence. But one way it's true and one way it's not true, and I'm struggling. Let me think. If the domain is non-trapping, then there's a strip where there are no resonances or scattering poles. But the other way around is not true. It's quite subtle.
Mm-hmm. The other question is just, does it extend to sound hard scatterers?
We haven't tried that, and it's not immediately extendable. Well, so it's not immediately extendable, but it's kind of open. I mean, we haven't really tried too hard.
Another question? Ari?
I might be slightly flying by the seat of my pants, but you have essentially a compact perturbation of identity. Sadly, it is not compact and self-adjoint or compact and normal, but still, essentially, a statement on coercivity is, to a very large extent, a statement on the spectrum or the pseudo-spectrum of the compact operator, which is not saying much because we know very, very little on pseudo-spectra of highly oscillatory operators of this kind. But there are actually some results on pseudo-spectra as k tends to infinity for some operators. Not this, but others, mostly by Henry Landau and others, But this sort of means that it might be possible, as k tends to infinity, to identify the pseudospectrum, the compact operator, which probably will be a circle or a disk. And then essentially a statement on coercivity is where is this disk in the complex plane, and what is the distance of this disk to the point
Yes.
1.
This was also addressed in Timo's talk, Timo Betke, 3 days ago.
Yes.
Addressed this. His
Right, this
range.
numerical range, yeah.
Yeah, that's numerical range
This
that I'm talking about. Okay, there's
It's
a
related.
relation to numerical range. I'm talking more about pseudo eigenvalues.
Okay, well, yeah, well, perhaps you can give me some references on that to see. Sounds very interesting.
Other question? Not the case, then let's thank Euan again for this C question.